Okay, so you're back for more resonance, I hope, because that's what we're doing here. We talked about resonance in the previous one. We laid down some ground rules and what is some allowed moves and stuff. Now we need to see how can we apply those moves to actually drawing resonance structures. Okay, so once again, this is going to be mostly drawing, so you're going to get to see a lot of the whiteboard. I'm going to flip that over now and we'll lay down some resonance stuff. Okay, so first of all, when we do resonance, let's write down our three moves again, right? Because I think that's a good place to start. We can go pi bond to lone pair. We can go pi bond to pi bond. Or we can go lone pair to pi bond. Right? And we talked before about what this means for sigma bonds. They don't participate and all that other good stuff. So when I talk about allowed moves and movement, you'll notice in the previous video that I started to use these curved arrows to show the flow of electrons. Curved arrows show movements of electrons. So, a couple rules about curved arrows. You always start from the location of your electrons. Right? We're thinking about electrons moving, and so we want to always start our arrow at, and when we're doing resonance, this will always be a lone pair or a pi bond. So let's go back to an example. Let's do, we'll do one the wrong way and then we'll do one the right way. So we did this example in the previous video, right, where I moved, oh, I want to take a pi bond and create a new pi bond. What I don't want to do, right, is move from the carbocation and move this over, right? This is bad. Do not do this. Do not do this, right? You will never start an arrow at a carbocation, ever, under any circumstances. Please don't, right? Um, you want to start your arrow where the electrons are. Carbocation obviously has no electrons. That's not where we want to start it. Instead, we're going to start from this pi bond. We're going to start our arrow here, and we're going to move our electrons so that they share with the carbocation. And so this is kind of the rule number 2, which was one that we mentioned in the previous video, and that's always move your electrons to a neighboring position. Right, or a neighboring atom. And notice that we're always going to be making a new lone pair or a new pi bond. Right, so if we're making a new pi bond, we kind of move the electrons in between the atoms that we want to make a pi bond between. So in this case, if I number off my carbons 1, 2, 3, and 4, I want a new pi bond between carbons 2 and 3. And so my arrow starts from this pi bond and moves to kind of the in-between area between carbons 2 and 3. Okay? And now I'm at a new pi bond, which is great. The other thing to keep track with what the curved arrows allow us to do is they allow us to do good bookkeeping of electrons. Right? It shows us, okay, I'm moving carbons away from between atoms 1 and 2, and I'm moving them to the position between atoms 2 and 3. And so what does that mean? Right? First of all, we can't make or break sigma bonds. No sigma bonds. Whoops. Hey, I don't want the eraser anymore. Made or broken. Okay, so we're good here. All we've done is break up. We've started from a pi bond, broke that pi bond, and made a new pi bond. That's allowed. That's rule. That's move number 2. We are okay. Right? When we do our bookkeeping, every arrow results in one atom losing electrons and one atom gaining electrons. Right? We're going to be well balanced. So there'll always be one position that loses electrons. There'll always be one position that gains electrons. So in our example over here, C1 is losing electrons, right? Because it had electrons that it was sharing as part of a pi bond, but in the resulting resonance structure, right, C1 no longer has that pi bond. So C1 has lost electrons. C3 is gaining electrons because, of course, it is a carbocation. Now it has a pi bond, and so that carbocation goes away. It goes from being positive to being neutral because we add negative charge. Now notice with C1, we're going from neutral and then we're losing electrons, so C1 should end up being positive, so there should be a carbocation there as well. So C1 loses electrons, goes from being neutral to being positive. C3 gains electrons, so it goes from being positive to being neutral. But of course, the overall charge here remains the same. We have a +1 charge across all 4 atoms here. We have a +1 charge across all 4 atoms over here. And this is the last and one of the easiest to overlook rules of resonance. The overall charge of the molecule always stays the same, right? So if you start with a compound that has a positive charge, you're going to end with a compound that has an overall positive charge, right? Now, I do want to go back to something that we drew last time and just kind of point out when we have something like this, this is neutral to begin with. When we break the pi bond and make a lone pair, we're creating charges, right? Notice that this carbon loses electrons because it had a pi bond and now it doesn't. So it goes from being neutral to positive, just like our example that I just did. But the oxygen gains electrons because it goes from having 2 lone pairs and a pi bond to now just having 3 lone pairs. So the oxygen goes from being neutral to being negative. Now we've created charge, but the overall charge in the molecule, this molecule is neutral on the left, and it's still overall neutral on the right. And so the charge overall remains the same. Same thing down here. We start with a neutral compound here. We end up with a neutral compound. Notice that the loss and gain of electrons is the opposite here. The oxygen loses electrons by giving up a lone pair to make a pi bond. So it goes from negative to neutral. And the carbocation gains electrons because it gains a pi bond. And so it goes from being positive to neutral. So hopefully you're noticing the pattern. When we have carbocations, we want to make pi bonds to them. That's how they are stabilized by resonance. That's what resonance does for us. So just wanted to make sure that I pointed that out. All right, so I think that's everything I wanted to draw and talk to you about. There'll be one more resonance video. It's going to talk about what makes a good resonance structure, what makes a stable resonance structure, and all that kind of stuff. Once we start moving electrons around and we feel like we can do that with some arrows, then now we need to know, once we've moved them around, have we done a good job or not? And so how do we evaluate that? There are lots of resonance worksheets. There's lots of resonance practice on D2L. Please make sure that you are practicing that and doing that and checking yourself against the answer key and asking me if you have any questions. Thanks.